Now, a relatively short lesson today. We have two types of function left that we want to look at. One is exponential and the other one is logarithmic. Now, both of these functions are what we would call inverses of one another. So I'm going to take them separately. I'm going to take exponential functions first. I'll do about 20 minutes and then I'll give you questions to do for the remainder of this class. And then we will take a look at the logarithmic functions. And again, a relatively short lesson, and I'll give you some questions to do on that. And once we have completed linears, quadratics, cubics, exponentials, and the final logarithmic functions, then we'll take them all together in a live class and make sure that we all understand what they are, how they're transformed, and how they're solved. So what is an exponential function? The word exponential is always used when we talk about the growth of a population. Okay, so whether it be a population of bacteria, whether it be a population in humanity, whatever it's going to be, they grow exponentially. So in other words, the basic number continues to add to itself. That is an exponential function. So if you start off with, say, one bacteria, because bacteria can divide by binary fission, 1 becomes 2, 2 becomes 4, 4 becomes 6, 6, 12, 24, and so on. And they begin to just multiply that way. And straight away you notice that over a short amount of time, you get a large amount of numbers. So let's say we start off with one bacterial cell. Yeah, 1 becomes 2, 2 becomes 4, 4 becomes 8, 16, 32, 64, 128, 512, and so on. All right, 516 I should say, and so on. So all of a sudden you notice that over, say, 1 to 8 steps, we have grown hugely in numbers. That is an exponential function. Okay, anything that grows rapidly and adds to itself, adds to the volume, that's exponential growth. I suppose in one sense compound interest would be the same. When you earn interest this year, next year the interest you earned itself earns interest. So you're building on everything year on year, and more about that in financial maths. Okay, so an exponential function have the form y equals ab to the power of x. Now a word about this, okay, because the values a, b and x are actually visible within the actual function. The first thing I want to say here is about the value of a. The value of a in every exponential function, whether it be the value of 1 or greater than 1, is always the number that the graph passes through on the y-axis. Okay, so keep that in mind. A is the number it passes through on the y-axis. Also, we can say that a is the number that's going to stretch it, but as we stretch it, it moves vertically upwards. Okay, so a will also cause a change in the vertical number. So if I, for example, if I move from a equals 3 to a equals 7, well then what happens is the graph that was a equals 3 was going through 3 on the y-axis. When I change the a from 3 to 7, it now goes through 7. So it's kind of called a vertical shift or a vertical stretch. Just watch for both of those words. What do they look like? Well, exponential functions always look like that. It's very, very similar to the graph I drew a moment ago, shape I drew a moment ago. You notice that there is slight growth followed by rapid growth. Okay, that's the sign of an exponential function. And by the way, a, as I'll tell you later on, ab to the x is always an upward growing graph. Whereas if we had ab to the minus x, it would start coming down. Okay, and I'll deal with those in a few moments. I'll show you an example of both of those in a few moments. Now, here's what I want to look at in this graph here. Y equals ab to the x. That's the form that it has. All right, but in this, I can see straight away what a and b are. There's a little bit of algebra involved to work out these values, and I'll do more examples of this later on. But first of all, we notice that it's going through the point 3. So immediately a is 3. So now I know that y equals 3bx. Okay, and all I need to work out b, because don't forget, one of the fundamental things of algebra is you can only have one variable if you want to work it out. So therefore I need an x and a y value. What I could do is I could simply look along here on the x-axis for a corresponding y. So there's a point, and there's an easy to read point. That point is a half 6. So that means x equals a half, y equals 6. Fill them in. 6 equals 3b to the power of a half. Okay, now 3, divide both sides by 3. 2 equals b to the half. Another word for the power of a half is a square root. And the way in which we get rid of square roots is to square both sides. See? So straight away, you've got b. Now I know what the function is. It's 3 times 4 to the power of x. That's what the function is. Now, more about that later, and I probably will repeat that example later on, but just to let you know that there's an awful lot can be taken out from an exponential function. When working with exponential functions, we need to remember laws of indices. Now, two that are very, very important. If you have the same base number with different indices being multiplied, then please remember that you keep the base and you add the indices or add the powers. If you have the same base being divided and you have, say for example, again, two different powers, then again you keep the base and subtract the powers. Okay? If you have a base with a power that's being raised to another power, now this is important, what you can do, because the brackets separate b and c, you can multiply them. It becomes a to the power of bc. And the final thing I want you to remember is anything to the power of 0 is 1. Now, they're the basic rules of indices that you would have met for your junior cert. Do have a quick look over them again. Make sure you understand there's 1, 2, there's 4 of them, okay, that I want you to remember. So keep those 4 in your heads. They're also in your book. You can take a look at them. Okay, whoops, a daisy. That's bad. Let's go back. Where were we? Here. Okay, so exponential functions, as we said already, are in the form y equals abx. Just like all other functions, they can be graphed and they can be transformed easily. So what does that mean? That means the following. Let's take a look at this. The graph ab to the x, for example, 10 to the x, what shape would it have? The first thing I know is this. It doesn't appear to have an a. It seems to have b. 10 is b, and then you've got the x. But what's the a value? The a value in this case is 1. So you could also say that this is the same as 1 times 10 to the x. Because now, here's what I know. This is a graph that's going to shoot upwards, but it's going to pass through the point 1. There it is. Okay, notice it shoots upwards and it's passing through the point 1. What happens when we've got a graph like this? Now, I spoke about this earlier. This is a negative power, okay? So this is 10 to the minus x. It doesn't give negative numbers. Again, I hope you remember from your indices, 10 to the minus x is nothing more than 1 over 10 to the x. See that? So therefore, it's still going to be a positive number. But in this case, because the power is negative, we've got a graph that comes downwards. And again, if you take this one here, let me just get rid of this. If you take 10 to the minus x, it doesn't look like it has an a value. So you just put a 1 in front. So therefore, it's going to go through the point 1, but it's going to come down the other way like this. So again, both of them go through the point 1. Why? Because 1 is the coefficient of the base. That's the base, that's the index, and the number that stands in front is the coefficient. So the coefficient will always tell you what number on the y-axis to shoot your graph through. And the power, if it's positive, will tell you to go up. If it's negative, to come down. But you still go through the power, or the coefficient that's in front of the base number. Both of these, as you can see, lie above the x-axis. So both of these functions can only give positive values. All right? Think about it. It models the growth of a population. You can't have negative people, you can't have negative bacteria. So it'll actually look after the growth going above the x-axis. And similarly, both of them, because both of them have the coefficient of 1, both of these go through the point 1, see? The only difference between them is whether they shoot up in case of a positive power or downwards in the case of a negative power. So let's take a couple of examples. I'm going to do quite a number of examples, but the examples I do, they are modelled on the homework that I've given you. Okay, so if you watch these and go over them a few times, you should have no difficulty with the homework. Here's a very simple one. Graph the function of f of x equals 2 times 3 to the x in the domain from minus 2 to 2. Now, again, use your trusty calculator. Turn on, if you know how to, turn on your table and graph your points. Put in your function as 2 bracket 3 to the power of alpha x. Okay, then close your brackets. Start at minus 2. Finish at 2 and take steps of 1. And if you do that, you'll get a table something like this. So there's your x value and there's your y value. So when you take your x and y values together, they are the couples that you're going to plot. All right. Now, here's what I want you to notice. Difficult to plot, easy, easy, easy. My advice, always plot the ones that are easiest to plot, because I already know that this is going to go through the point 2 anyway on the y-axis. Okay, so you're going to move from minus 2 on the x-axis to plus 2. So that means equal parts of both sides of the x-axis. And you can then run the y-axis. Notice there's no negative y's. So you can just run the y-axis down and put the x-axis at the bottom, like an inverted capital letter T. Something similar to this. And when you plot your points, that's the point you get. Now notice, all we did was plot these. See? So there's the first one, there's the second one, and there's the third one. So you get an idea now as to how to sketch your graph. And you run it through there, down into these 2 points here. If you can, and they're easy enough to plot, you can plot them, okay? But the ones that are easiest to plot give you an idea what the graph looks like. Any ones that are difficult, I plot the easier ones first, and then try and fill in the more difficult ones when you get an idea of what the shape of the graph is like. So that's what you're asked to graph, and I've given you a few of those to do. Okay, another one, page 149, in work example 618. The following graph show the graph of the function a, b to the x. Work out the values of a and b. Now I did this example already, but I'm going to do it here again. So here's all I know. It's a, b to the x. So y equals ab to the x. The question says work out the value of a and the value of b. But here's what we know. The value of a is automatically the number that the exponential graph goes through on the y-axis. So immediately I can see here that a is equal to 3. So now that I've discovered that, let's go back and fill it in. Y equals 3bx. And if I want to find b, I have to know x and y. So therefore, on the graph, I've got to pick a value that's easy to read and easy to use. And that value, as I showed you in the previous time I did this example, is this one here. There's one that's easy to use. Because if you notice, that point there is the point half 6. See that? It's the point half on the x-axis, 6 on the y-axis. You always put your values in alphabetical order. X value first, y value second. Which means x has a value of a half, y has a value of 6, and because they belong to that graph, that function, they can be fitted into its formula. So y is 6 equals 3b to the half. Okay, divide both sides by 3, 2 equals b to the half. So therefore, to get rid of the power of a half, you square both sides, because don't forget, b to the half is exactly the same as the square root of b. So in order to get rid of a square root, we square. So you square both sides, and that gives you 4 is equal to b. So we can take these two values back up here and write down the functional form as y equals 3 times 4 to the power of x. And that is that function there. So they're quite simple, quite straightforward. You'll automatically find the a value by seeing where the graph goes through on the y-axis. And all you've got to do then is pick a point on that graph that is easy to read, take out its x and y value, slap them into the function, and work out the value of b. Okay, what about our transformations? So we've done these before, so these shouldn't be new to you. We know how to work out transformations. They might be just a little tiny bit different here in dealing with exponential functions. So let's take a look at them. And I'm going to do this from the point of view of taking 4 examples. Okay, I'm going to do them all in the one question because they're easy enough to follow. Shown is the graph 4 to the power of x, and the red one is 4 to the power of x. So there it is. Okay, also shown are 3 times 4 to the x, 0.5 times 4 to the x, 4 to the power of x minus 2, and then the difference, 4 to the power of x plus 3. So that full thing there is a power. Okay, let's start with the first one. What do you notice? If we remember that they are a, b, x, and that a is the number they go through on the y-axis, well then I can see straight away that this one here is the one that goes through the point 3. So where's 3? 1, 2, 3. There it is. So that black line is 3, 4 to the x. In other words, what was the original red function has been stretched upwards or shifted upwards to its new resting point of 3. What about the next one? A half times 4 to the power of x. Now again, take the form of the function. This is the graph that goes through the value of a half on the y-axis. So where's that? Well, if that's 1, there's a half. There it is. So that blue line is the one 0.5 times 4 to the x. So they actually get quite easy. If you remember that the a value in all these functions is the point that they go through on the y-axis. They're easy to spot. The next two are a little bit more tricky, so let's pay attention to those. Okay, 4x minus 2. Now it's 4 to the x, but then it's minus 2. And minus 2 is a constant, which simply means that the original graph has been dropped down 2 spaces. Okay, now where's the original graph? There's the original graph in red. That has been dropped down 2 spaces. So there's 1 space, there's 2 spaces. So the only drop that corresponds to 2 spaces is the green one. So this one here must be 4 to the x minus 2. And finally, by process of elimination, if you want to, you can simply say, well, that one there over there must be the last one because we haven't talked about that one at all. Okay, or do the following, might be easier. 4 to the x plus 3. Now remember what I told you. When x has a number directly involved with it, see that? Take it out, set it equal to 0, solve it, and then it's telling you that the original 4 to the x, the red one, has been shifted back to the left 3 spaces. Now take the red one, that's gone back 3 spaces. So obviously if we want to go back 3 spaces, we're going back to here. There it is. So that one must be 4 to the x plus 3. Notice that plus 3 is part of the power. Down here minus 2 is a constant. So there's a slight difference between them. Okay, so let's just go through those again very quickly. 4 to the x is shown. So there it is. That's 4 to the x. Okay, now the next one is 3 times 4 to the x. The first coefficient is the point it goes through on the y-axis. There it is there. So that one is 3 times 4 to the x. Okay, next one, half times 4 to the x. It goes through a half, and the only one that's going through a half is this one here. So that's 0.5 times 4 to the x. Okay, the next one is 4 to the x minus a constant, and the constant always gives us vertical shift. Okay, so that means that the original 4 to the x, which is the red one, is dropped down 2 spaces. So this one here must be 4 to the x minus 2. And finally, if we take the x plus 3, set it equal to 0, as we always do every time there's a number involved at x in functions. We set it equal to 0 and we solve it. So x equals minus 3, which means that the original 4 to the x has been shifted back to the left by 3 spaces. And the only one, take that red line there, yeah, the only one that looks like it's been shifted back 3 spaces is this one here. So that must be 4 to the x plus 3. Now again, you can go over that video as much as you want to see to make sure that you have them, because there are some questions coming up that will ask you about these changes and these transformations. Worked example question 22, page 152. The graph of the function y equals 2x is shifted to the left by 2 units and shifted upwards by 3 units. What's the new functional form? Now, y equals 2x. What do we have? It's shifted to the left. So we've got a left movement of 2 units. Now, what does that? 2 units to the left means, because it's a horizontal shift, that the x has been affected directly. Okay, so horizontal shift by a backward movement of 2 units puts a plus 2 immediately after the x. You might say, why is that? Because if I take out x plus 2 and I set it equal to 0 and I solve it, see, that's where the minus 2 comes from. That's 2 units back. So if x is equal to minus 2, which is going back to the left, then x plus 2 equals 0. So you put a plus 2 after that. That's the first one. And is shifted upwards. So it's going up by 3 units. Okay, so it's going up by 3 units. Now, the only thing that can cause a vertical stretch or a vertical shift upwards is the a value. So the only thing I do then is I put a 3 in front of the whole thing like that, and that is the new functional form. So what was y equals 2x, watch it again, first of all, has been shifted to the left by 2 units, and then has been moved vertically upward 3 units. Meaning what? It's going to go through the point 3, or 3 units above where it already was. That's it. Okay, so that's how easy these things are. Page 151, question 13. An economist estimates, so these are real life questions and you've got some of these to do as well. An economist estimates that the population of a country will increase by 25% every 10 years. And the population is 15 million in 2012. Okay, now, I need you to be careful with this. Number 1, if x represents the number of years since 2012, define a function p in x that represents the population of the country. Okay, there's a bit of a hint in there. P. Now, when we're dealing with growth, okay, because we are dealing with a population and we're dealing with growth. Bacteria grow in size over time, people grow, population grows in size over time, but so does money. So in your tables, let me just reach down here and get my trusty tables. There is a formula in your financial math section, if I can find it now, which represents the growth of money over time. And there it is. Maybe you can see this or not now. It's the very first formula there. F equals P times 1 plus I to the power of N. Okay, that represents what we call compounded growth. It represents population growth. It represents money growth as well. But notice there's a P in there. That is the formula that they're looking for. So if X represents the number of years, then define a function P in X that represents the population of the country. Okay, so from our tables, what do we know? From our tables, we have a growth formula. It's on page 30 of your tables. And here it is. The final numbers will be equal to the present population multiplied by 1 plus I to the power of N. Now, N is the number of years, but in this question here, they've told me to take X as the number of years. So therefore, it'll be F equals present population 1 plus I. I, by the way, is the percentage growth, okay, to the power of X. And that's the formula that they're looking for. Now, unless I had told you it was in the tables, you wouldn't have got that. But it is in the tables. It's the growth formula. Page 30, the compound interest formula. It's not just for money, it's for population, and it's for anything else that grows on top of itself, okay? Okay, so I have this done out. So the current population will grow. So we need to develop an exponential function to multiply the current population. Now, here's another thing I want you to remember. See at 25%? 25% is a symbol. It's not a mathematic. You can't use it mathematically. You always have to change a percentage into a decimal. So 25% is 0.25. Okay, so keep that in mind. And that would be the growth. It's increasing. So that would be the growth. And that's what I have in the next sentence after the formula. The present population is 15 million in 2012. That's what it's telling you. Okay. The rate of growth is 25%, which is 0.25. We never used a percentage. We always used a decimal. And N is the number of blocks of 10-year cycles, because that's what they're telling you here, every 10 years. So we end up getting a formula of, remember what we said, F equals P, there it is up above me, or to the power of N, or I, whatever you want to put in there. F is the final number, so that's F of X, equals the present population in millions. Well, how many million at the beginning? There's 15 million now. So you put 15 in there, representing millions, times 1 plus R. R is the percentage growth, which we said is 25%. We don't use that. We use the decimal form. So it's 1 plus 0.25 to the power of N. And that's what you end up with here. Now, they ask you for 1 in terms of X. So F of X is equal to 15 by 1.25 to the power of X, where X, as they say already, is the amount of years that we're looking at. X is time. So that's the function. Second thing says, draw a graph to show the estimated population growth for the next 50 years. Now, you can do that because once you have your function, you go back to your calculator and you put in 15 times 1.25 to the power of alpha X. Now, it's over 50 years. Start at 0, go to 50. Oh, sorry, go to 5 because it's in blocks of 10, isn't it? Yeah, every 10 years. So therefore, start at 0 and go to 5 and do it in steps of 1. Get your table on your calculator, and then if your table is correct, your table should look something like this. So there's 10 years, 20 years, 30 years, 40 years, 50 years. Okay. So when you put these values in, don't bother putting in 0, start at 1. You end up getting this number of million. So we start off at 15 million. So 0 would be 15. Okay. Then it grows to 18.75, 23, 29. See how the population grows hugely over a short number of steps? That's the power of an exponential function. So they're your couples that you have to plot on your graph. Now, you have to do this as best you can. All the X values are positive, all the Y values are positive, so therefore you're simply dealing with the first quadrant. That's what you're dealing with, okay? If the X's are positive and the Y's are positive, you're going to deal with only positive Y's and positive X's, so only draw that section of the graph that you require. And you get something like this. Now, what's along the bottom? This is time in blocks of 10. And what's this one up here? This is the population in millions. So always make sure that you label your graphs. Okay, and what did the question ask me in the previous one? It asked me about something at the end of that. If I can go back, I'll come back to that in a moment. It says, use your graph to estimate when the population will reach 25 million. Okay, well, first of all, where is 25 million? There's 20, there's 30, so that must be 25. So I run across until I hit the graph, and I drop down. And I find out that it is 2.2, okay? Now that's 2.2, because don't forget there's 5 boxes between 2 and 3, so that's 2.2. However, they are in blocks of 10 years. So you multiply it by 10, and you figure out that in 22 years' time, you will have a population of 25 million. So they're not that difficult. They are quite easy to do. You just need practice and plenty of it. Okay, so I have those lines drawn on the graph there. You find your 25, and over you go, drop down, and you get your 20. Now I said 22, but again, that's accuracy for you. So we ended up with 25, population will reach 25 million in, as we said here, 2035. Is that right? 2035, yeah. So you can actually see what it is. That's 2.2. So 2.2, as I said already, that's 22 years. Unless you add it on to the present, which is 2012, and that gets you up to nearly 2035. It's 2012, which is the moment here, plus, as I thought, the 22 years. So you add that on to where you're starting, and you end up getting 2034. Now, it wouldn't be too far, and there's a margin of error either side of the actual answer, so 2034 would be fine as well. Okay, over to you. Little, as I said, relatively short class today. I want you to take a look at these questions. All of these questions are based on what we've just covered in class on the exponential functions. Tomorrow, logarithmic functions.